The delay, but welcome everyone to October Fundamentals. Pardon my throat, it's a little scratchy. So today we're going to be talking about observing the planets. This is something that I've really enjoyed throughout this hobby of mine because they're objects that are very easily accessible in the sky. You don't have to travel to a dark site to see them. You can go right to your backyard. And there's something that really change a lot fairly quickly. So there's always something new to see. So they're very rewarding objects to take a look at. So they're easy to get to and very rewarding. So here I got a clicker. So with that intro, then let's get started. Let's see.
Hang on a second.
Okay.
There you go. Is it working?
Let's see.
It's not you, it's it.
No, so which, oh, do I have to aim it this way? Or which way?
Yeah, it's only one of
Yeah.
them.
It's these two right here.
Okay. Here we go. Okay, cool. So to get started, if we go out and look west right after sunset, what's happening right now is you're going to have the inner planets that are visible. This is a view that would be the middle of next month, middle of November. So then you'll have Venus kind of up over the horizon here, and Mercury right below it in between Venus and the horizon. So you look about 45 minutes after sunset, you'll be able to catch both of these planets. If you go out right now, you'll be able to see Venus a bit lower in the sky, but not Mercury yet. But Venus being incredibly bright is going to be kind of easy to catch with your eye, and then you can use that as a guide to help you get to Mercury starting next month. Mercury doesn't get terribly high over the horizon and doesn't last long in being in a good place to get it. So you'd have just a smaller window to observe it, but it's really cool if you can see it. So here are some drawings I made of Mercury when I observed it. You see then as it goes around the sun, and from where we are over there, that it's going to have phases. So when it is furthest from the Earth, then it's going to be nearly full, and as it swings closer, then it'll get larger in apparent size, but also the phase will change and will move through like the phases of the moon from first quarter to crescent. So here I happened to catch it when it was at like a kind of quarter moon phase, if you will. I caught it in the evening, which is the first drawing, and then a couple months later when it was high in the morning sky, and then it had the flip, like you're going from a first quarter moon to a last quarter moon. So when we observe it in November, it's going to be a little more of the gibbous phase, but it's still kind of cool to see. So if you can check it out, then do so. Now Venus will also have the same kind of appearance, but because it's further from the sun, we get to see it for a much longer period of time and get to see it better. So here are some observations I made of Venus back in 2012. And so I point this out because if you can see it starting now or next month, that's a good time to do it. If you just have a one-off, like you look at it once, it'll be, all right, it looks something like the moon, it has a phase. But it really gets interesting if you're able to check in on it over time. So as I did here, so I would look maybe a couple times every month. And as I did, I was able to notice not only the phase changing, but also this apparent size as well. And once it got really close, it was much larger than when I started, much brighter, but a really thin crescent. So it's much more rewarding to look at Venus if you look at it over time. So a good thing to do is look at it in your telescope, try and gauge the apparent size in your eyepiece, just make a mental note. And then when you check back on it, see if you can notice it really growing, getting bigger. And then you'll see these phases all sweep out. So we're going to have the same type of thing taking place. And if you can start viewing it now or next month, starting next month, you'll be right at the beginning kind of portion. So that's something I think worthwhile. And it's kind of easy to find and to look at. So next is Mars. So this is the path that it's going to take in the sky. It's somewhere over here now in October, right there. As we keep looking at it in the sky, we'll be able to see the retrograde motion. So that's another thing you could do. You've got Pollux and Castor, really bright stars that can be reference points. And you can check in on it like you do with Venus from time to time. And you can notice how Mars is moving across the sky relative to Pollux and Castor. Next I want to show our opposition. So Mars has a very eccentric orbit, and so because of that, it's much closer to the Sun at one point, which would be the southern hemisphere summer, than it is at the other point, which would be the northern hemisphere summer or southern hemisphere winter. And as it lines up with the Earth, it means it's much closer at a perihelic opposition than an aphelic opposition. So we had the best view of it in 2018 and 2020 when it was around here, and now it's swung up to where it's going to be in January over here. So when it moves to here, the seasons change. It has seasons just like the Earth because the axis is tipped in a very similar way. So it's going to be, here it was a solstice for the north and south. Here it's going to be near equinoxes. So you're not going to have one hemisphere or the other particularly favored. And as a consequence, the polar regions will look a little different. As the planet's transitioning from summer to winter in the south and winter to summer in the north, you get clouds forming at both poles. So I had a couple drawings I wasn't able to bring up with Mars, so I'll have to describe it. So even though this is not the most favorable opposition, it's still something that can be extremely good to take advantage of. For example, when Christian Huygens first observed Mars in the 1650s and made the first discoveries of the actual surface features, he did it during an opposition much like this one rather than a closer one, which you would think at first. And when I first began observing Mars in 1975, it was a similar opposition, also a winter opposition. And so in spite of the fact that it wasn't as close as it can get, it was still good enough where you could get a good sense of the surface features just by looking at it. So what could happen for you if you're not familiar with Mars is you can look at it and start to get familiar with the surface markings by observing it. And you could do it in a similar way then as Huygens did, where we're not going to get great resolution, but we don't need to. So when Huygens looked at Mars, he noticed something he called a somber band. So that is just a swath across the southern kind of temperate region of the planet that went all the way around the planet. So that's where most of the dark markings are, dark contrast markings are, that are the surface features. And then one feature in particular flowed out from that band, and that was a triangular shaped feature, and it's now known as the Syrtis Major, and that's the most prominent feature on the surface of Mars. And so Huygens discovered that feature with a drawing he made in November of 1659. So you yourself then can, like Huygens, get yourself familiar with the basic surface features of Mars just by looking at it in the course of the next upcoming months. So middle of November, it'll get to be about 10 arc seconds across, which is where people can begin to see some details on the surface, and it'll stay that close for the next 4 months, getting a little bit better by the opposition in January. So you could already start viewing next month, and you'd have about 4 months altogether to check in on it from time to time. So when I did my first drawings of it, I had a 4¼ inch Newtonian reflector, so a very simple scope, and I was 15 years old, but I was still able to see the Syrtis Major, the somber band that Huygens described, and even a feature in the northern hemisphere, which is called the Mare Accidalia, and that's the most prominent feature in the north. And I even noticed that that feature slanted to the east at what was like the top of the tip of that marking. So now, nearly half a century later, if you were to look at it, you'd see much of the same, but the Mare Accidalium is going to be different. It'll be mirror reversed now from what I had seen back then. So an important change has taken place on the planet. And it's kind of, the more you study it, the more interesting that becomes, because we thought at first that these dark markings represented true contours of the surface, like oceans and continents. And Schiaparelli made the first modern maps of Mars in the 1870s and gave the names to these markings that we still use today. And he followed in the tradition of the moon, where he called the dark markings seas and the brighter regions continents. So with the moon, there is a truth to that in terms of actual topography. So the Sea of Tranquility, for example, really is a basin, low elevation, dark, low, while the surrounding highlands are bright and true highlands. So it was surprising when we sent probes to Mars that these dark markings don't match the actual contours of the surface like they do with the moon. It turns out they're draped over the actual topography. And so that's something, of course, that's surprising. You wouldn't, expect, why would that be? So a marking like the Syrtis Major turns out to be a shield volcano. It's very wide, but not terribly tall, but it's a mountain. So you could sort of understand why it would be dark in appearance. But that other feature I mentioned, the Mare Accidalia, looks similar to the Syrtis Major. It is very dark also. It's in the northern hemisphere, but it's in the middle of a vast plain. So there is no reason by topography that that particular part of the plain should be dark to begin with, but it is. And it persists over centuries that way. So we know that these contrasts are caused by winds that move dust around the surface of Mars, kind of sweeping brighter dust away from a darker volcanic surface. But why they would sweep to keep markings so permanent for so long is kind of a mystery. And then when you see changes occur, like the one I described, you would think at first that would be a random change, the wind blowing, moving the contrasts around. But when you look at the historical record, you see that astronomers in the past, particularly for this marking, had seen it, that kind of strange westward slant, all the way back in 1905, and continued to see it that way through 1909. And then that kind of faded out, and the current thing I had been seeing for years took over, and now it's reverted back to that old position. And in fact, as I've gone over all my drawings of Mars over the years, you'd see that general features keep the same topography, the same appearance, but there are still subtle changes. So every opposition is a little different. And each of these changes that you see always relate back to the way someone had seen it before. So for example, the initial slant I saw was how astronomers like Schiaparelli had seen it, and I felt good, hey, I'm validated with what I'm seeing. And then this change that seems random isn't really random. Hey, that's how some other astronomers had seen it at another point in time. So that's also really amazing, right? That these things will change, but not change randomly, even when there's no topography that would like cause that to happen. So there still are some mysteries about Mars. We're slowly starting to understand how this could happen, having to do with weather patterns influenced by basins maybe 1,000 miles away from the features themselves. But we still have a lot more to learn. So the upshot is, if you can get out and look at Mars, first try and just get familiar with the features you can, even with an opposition like this. Make a note on some of them of how they look to you, and you will be rewarded over time, because every opposition, it'll look a little different, and you'll be able to appreciate those changes more now that you've gotten a bit familiar with the markings themselves. So I just wanted to point that out for Mars. So now let's move on to the gas giants. So these are going to be well placed for us to view. We start with Uranus and Jupiter. So they're going to be in the constellation Taurus. So Jupiter is by kind of the horns of Taurus. This is where it is at the beginning of this month. It's just all too easy to see, unmistakable. Just go outside, find Taurus, and there it is. Uranus is just below the Pleiades. So it's kind of, you can use them to help guide you to where Uranus would be. But since Uranus is not something you'll be able to pick up with the unaided eye, at least from these guys, you need to go online to like a sky and telescope site, and then you can get something a little more detailed to help you pick it out from the background stars. So we'll start with Uranus. So what would it look like if you look through your telescope? So here is a drawing I made back in 2009. And you notice the disk you can resolve its disk. It's going to be about 3.5 arc seconds across. And you even notice color on it. Everyone will see color a little differently. So I saw it as kind of greenish. Other people could see it more bluish. So you can see for yourself, how does it look to you in terms of the color. You also notice the shape. It's not circular, it's kind of oval, squashed. So all the gas giants are noticeably squashed that way. So they are all much larger than the Earth, and they spin a lot faster too. So Jupiter, for example, is 11 times the diameter of the Earth and spins more than twice as fast. So all the other gas giants too are large, spin fast. And when that happens, the mass gets thrown towards the equator, and it causes this noticeable oblong shape. So that's one of the things you can do for Uranus, is just notice the color, notice the shape. Then I always am a fan, as you can tell by now, of checking in on them from time to time. So here I looked at it over a period of just 24 hours, thereabouts, and I could notice how it already is moving with respect to the background stars. So that makes it kind of interesting too. So there's something you can do with Uranus. So Jupiter is something that will really put on quite a show, not only the planet itself, but also its moons. So there was a couple of years ago, I did a trip out to Cross Timber State Park in Kansas. I didn't go there to look at Jupiter. I went out there to do deep sky observing, so I could get away from the lights. But since I'm there, since Jupiter was up in the sky, I'm always going to check in on Jupiter in between doing my deep sky observing. And it was actually very rewarding. So I was there 3 nights, and then I made sketches of, just what the moons looked like over those 3 nights. So if you go out and look at Jupiter, you will see a similar thing. So if you go from night to night, you'll notice that the moons are not in the same place. So here it happened to be, you got 2 moons on one side, 2 on the other on the first night. Then the second night you see 3 on the western side, 1 on the eastern side. And then the third night, just one on the western side, three on the eastern side. So, they shuttle back and forth. This is what Galileo had seen when he first looked at Jupiter with his telescope. So I added these lines, and they show then why they're moving the way they do. This moon here, Callisto, is the outermost moon. It had just been in front of Jupiter not too long ago, and now is taking this slow arc away from the planet. Ganymede, the next moon out, was over here. It had just then passed behind Jupiter and then was making its arc the other way, the other side of its orbit. And then the other two, Io and Europa, are closer in and are just sweeping around in shorter periods around the planet. So also there was something interesting going on over here where the moon disappeared for a little bit. And so we're going to take a closer look at that now. So here is the drawings I made on the first night of looking at Jupiter. So I started at what was 0 hours universal time, about 6 p.m. local time. And that's what it looked like. So you had the four main cloud belts. These drawings I'm doing are done as a Newtonian telescope would show it, or any telescope without a diagonal. So that is, south is up and north is down. And therefore, with this upside down view, as you typically see it in a Newtonian, so east is going to be to the right and west to the left. If you see things the proper way, then it's all reversed. North is where it should be and west is to the right. So all the drawings I have will be, which had been kind of a traditional way to do it for many years, to just show them south up like your telescope would typically show it. So this would be like what you can see very easily. So what you have here being reversed, of course, the south equatorial belt, the north equatorial belt, and the north and south temperate belts. So if I just did a one-off and did that and said, fine, I saw Jupiter, I'm done, let's see something else, then I would miss out on a lot. So I noticed first, just 15 minutes after starting my viewing, that Ganymede appeared from behind the planet. And so that's something that's really cool to see, this star-like object just appearing before your eyes as you're looking at the planet. So I then caught that, then I moved away from Jupiter, did my deep sky thing, and I came back a couple hours later to check in. Now, I saw Jupiter looks really different in just a couple hours because it's rapid rotation. So now the great red spot has rotated into view, into the center of the disk. It happened at this time to be accompanied by another spot at the tip of the northern equatorial belt. And then Ganymede had noticeably moved away from Jupiter in that time. Then I kept looking at it for the next half hour or so. And then what happened was Ganymede moved into the shadow of Jupiter, and then I saw it slowly vanish before my eyes. So first I got to see it appear, now I got to see it vanish. So that's really cool. It just is beautiful to see. And it took about 4 minutes for me to see it fade completely from view. Right? So then also you notice how the red spot and the northern spot have also shifted in position, really showing this rapid rotation of Jupiter. So this is why it's rewarding to go look at Jupiter. You can just set your scope out, take a look at it, go back inside if you're at home, watch Netflix for a little, whatever, come back, check in on it again. You'll be rewarded with all these changes in just a short period of time. So another important point to point out is, how do we know when these events are happening? Because certainly I had knowledge that this would be going on, so I could plan these views. Well, we belong to this club, so we have one thing called Rick's Picks, right? And Rick has in his current picks that there are phenomena of Jupiter's moons to look at. In fact, tonight there's going to be, according to Rick, the same thing. Ganymede is going to have an eclipse go into an eclipse tonight, about 11:30 or so tonight. Not only Ganymede, but the moon Io is going to do that as well. So if the weather will cooperate tonight, you might be able to, to catch it tonight. In addition to our own club resources, there's also online resources like Sky and Telescope, and you can just look them up, and they have observing tools that also describe things like the phenomena of Jupiter's moons, and even when the red spot would be visible. So those are good resources, so you can kind of plan your viewing. But you can see this is very rewarding to take a look at Jupiter, even over brief times. So another phenomena that happens with Jupiter is shadow transits. So here I made some drawings of Jupiter when there was more unusual, a double shadow transit. So this is just to show you what a shadow transit looks like. So in the top image at 4:55 universal time, the two of the shadows fell across Jupiter, and you could see a spot at the equatorial region too. And as we just flow through the drawings, you see how Jupiter is rotating, that spot is moving, and these shadows are sweeping across the planet. They're moving too, until they both move off the planet, and that's just a couple hours later. Also, you see the moons, and they're shifting in this very brief period of time. And so the configuration that we end with is really different from the configuration we began with, and that's just 2 hours' time. So this one is Callisto, and it happens to seem not to be moving because it was just entering the apex of its orbit. And so it was first sweeping kind of to the peak and then just sweeping a little past its peak. So it had this illusion like it wasn't really moving when in fact it was. The others were just in more obvious parts of their orbit where you could pick up their motions. But again, this shows how rewarding Jupiter can be in just looking at it over a couple hours one night. And if you catch a good night where there's something with the moons, it's really beautiful to look at. So here I wanted to throw out some observations I made back in 1982. The drawings I showed you so far were made with my current scope, which is a small 4.7-inch, 120 millimeter refractor. It's not really a planetary scope. I got it more to do my wide field, deep sky observing. But you can use it for planets with the right eyepieces and filters. But it never will get great resolution on planets. It's not a true planetary scope. If you have a true planetary scope, much more detail emerges. So these are made when I was in college, and I was able to use the University of Illinois' 12-inch refractor. And boy, was that a planetary scope, if there ever was one. So you see many more features then emerge. And so you can take this in, however much you want. The simple views are very rewarding, like we just saw. If you get into imaging these days, then you can really get incredible details. So you notice a spotlight here in between these two darker things. I've seen images now, people posting their imaging from Jupiter that is so good it's resolving little clouds within this cloud, and it's actually showing rotation in these spots. So you as an amateur can now do imaging on planets and create movies showing these spots as true anticyclones and cyclones, actually with features moving and rotating. So it's amazing what we can do today, right, with technology. And so that's just up to you. If you want to get into imaging, it can be incredibly rewarding that way. The red spot as well. There are many people who post their images online of the red spot and show how the red spot is rotating, because you're getting resolving details to such a fine degree. It's fantastic. So here, even with just my eyeball astronomy as I did at that time, just by seeing many more features, I was able to track them over time, and I was able to determine how the different jet streams on the planet were moving. So I would notice that some jet streams moved faster than others, and I was able to infer from that how the red spot is between two opposing jet streams, and so must be rotating like a wheel between opposite moving forces, which in fact it is. So even with drawings, you could get a sense of motion if you get more involved, right, with your observing. So one last thing I wanted to point out here is at this time, in 1982, there were, we want to talk about longevity of these features. So the red spot is one that has been seen for centuries, but the other spots, almost all the other spots, are short-lived features, usually a year, sometimes two, that's about it. And so only the red spot is a really long-term feature, but there is one other class of features that last a long time, and that's these. This is again south up, so these are south temperate ovals. So this was, according to NASA, 3 of these particular spots were important. They were the only spots we have observed how they formed to begin with. So it was back in the 1930s that astronomers saw an unusual outbreak on Jupiter that then coalesced into 3 anticyclones. And then they were between like rods, for better term, like this. And so they called the rods, AB to note like, here's A, here's B, then B, C, A, B, C, D, E, F, right? So that's how they named the rods, and then these features formed at the breaks between the rods. So then the names that the rods disappear, and the names that the cyclones took on was then F, A, B, C, and D, E. So that's how they got these unusual names. And then all 3 were seen since 1939, and they were seen then all thereafter for the next 60 years. And so here I got myself to be able to see those particular important storms, and even a 4th one in the South Temperate Belt that was much shorter lived. So we'll get to those in another minute, those long-lasting ones. So here, the last thing I'm going to touch on with Jupiter is just not only the rewards you can have by looking at it over a short period of time, like 2 hours, but the rewards you get then once you get enough records over time, right? And this is still simple observations, not super detailed, but still very rewarding. So if you start looking at Jupiter and you make some notes and observations, then that will be so rewarding for you over time as well, because it does keep changing, and you'll be able to appreciate those changes so much more, because it'll be from your own observations. So here is one from 1975 that I made with my little reflecting telescope, and look how magnificent the red spot was back then. Oh my goodness. And then in a short period of time, by 1982, something dramatic happened with the red spot. It really faded dramatically, and it was really hard to pick up. Then it took till about 2010 till the red color started to come back. And when it did, look now, it's shrunk, right? And so now it's much smaller today than it was back, in the 70s. So we have changes in the red spot that we notice. What's going on is it's changing both horizontally and vertically. So horizontally, obviously, because it's shrunk in its diameter, but also vertically by virtue of the color. So they believe that the color of the red spot comes from it rising high into the atmosphere of Jupiter. In fact, it's the biggest high pressure area on the planet. When it really gets up there, it will interact strongly with sunlight, and the sunlight will create a chemical reaction with sulfur and phosphorus within the clouds of the red spot, and that will create these bright colors. But as it sinks back into the planet, then this effect is diminished, and so the colors fade. So that's kind of cool. So we see then it changes over time. It's really a storm system that's continually changing, so that's why you want to keep checking it out over time to see what happens. So we'll see what happens in the future. Is it going to continue to shrink? Is it going to start to expand again, as some astronomers believe it will? What's going to happen with the colors? So that's what makes it interesting to keep following. And then the last thing here is we see a south-temperate oval over here. So the three that I talked about before, well, they lasted 60 years, and then they began to merge. No one knows why. They were, for 60 years, they would kind of move close together, but then bounce away. And then all of a sudden, for reasons we don't know, then they started to merge instead. And so from 1998 to 2000, the three spots merged into one big one. So this one is now known as the Red Spot Junior, and also officially BA is its designation. So that's all that's left from the original three. And it'll be interesting to see how that spot progresses over the years. And it was also rewarding for me because I had seen, the precursors to that current feature. And so this is all available to you, right? To look at it, to see these spots, and then to watch how they change over time. All right, so now we're going to move to the last two planets that will be visible in the sky, Neptune and Saturn. So Saturn has come into opposition a bit earlier than Jupiter. So both these planets are near the circlet of Pisces, which is not shown well, unfortunately, in this slide here. Neptune's more directly under the circlet, and Saturn a bit to the side. And because Saturn's a bit to the side, it's kind of a kind of border area between two constellations. But Saturn, so you look to the circlet of Pisces, and that will direct you certainly to Saturn because it's so bright. Can't miss it. And then Neptune, you used to have an idea from the circlet, like you did with the Pleiades for Uranus, of where to point the scope to get to Neptune. But as with Uranus, you should consult something like Sky and Telescope online to get a better idea of how to pick it out from the background stars with your scope on the particular night you're viewing. So let's start with Neptune. So here are some drawings I made in 1976, and that was the first time I saw it. So I was 16 years old at the time. So Neptune was discovered through mathematics. So you had two astronomers noted that Uranus was not moving the way it should in its orbit. It seemed like something was tugging on it. So two mathematicians, Adams and Leverrier, independently calculated, based on how this Uranus seemed to be tugged, where this unseen planet might be. And then they both submitted their data to their respective organizations, and then those organizations dragged their feet. So then Leverrier got impatient, so he reached out to a friend of his at the Berlin Observatory, and Johann Gall. And so he said, hey, Johann, if you look in this part of the sky, you should be able to discover this new planet. So Johann went out, he had a star chart, and then he looked at, matching the stars in the star charts to what he's seeing in the eyepiece, and then it was like, oh, there is a star that does not belong, so that must be the planet, and in fact it was. So I was sort of, in my way, trying to recreate that experience when I was 16, where I got the coordinates of where Neptune was, and I got a star chart, and then I was looking first to see if I could match the eyepiece view with the chart, and then see if I could pick out Neptune, and eventually I was successful. And then I drew it again like a month later just to see, it's shifted its position among the stars. So now many years later, I have a much better telescope, and then I'm able to resolve the disk of Neptune. so with high power. So it's only about 2 arc seconds or so across. It'll be about 2.5 arc seconds now, so you'll be able to get a good look at it. So any good telescope, you'll be able to see the disk of Neptune. I can't really tell if it's flattened or not because it's so small a disk. See what you can do. But also color, so it looks bluish to me. You can see for yourself, how does it look to you? Is it bluish or greenish? Because different people will see colors a little bit differently. But it's, I saw it again at Cross Timbers when I was there, and I remarked in my notes that it reminded me of a planetary nebula, like the blue racquetball. So just this gorgeous color and nice little disk. So here I made observations a week apart, and I could notice how Neptune is moving across the sky, but within the same field. You see the same field stars, but now it's moved across the sky in that time. But this is in a whole week, so it's not moving very fast even compared to Uranus, where the motion against the background sky was much more obvious in just a day. So these are things you can do with Neptune. So now we'll go to Saturn, and that's our last planet we're going to cover tonight. So I'll start, as I did with Jupiter, with the moons. So Saturn has 6 moons that you can see with a small telescope. There are 4 of them with our Tethys, Ione, Rhea, and Enceladus, and they're really close to Saturn. And when I look at them through a telescope, it reminds me of like looking at bugs flying around a light, right? So they're small, but you can pick them up. Enceladus is the one closest to Saturn. As you can see, it's marked by the E. And it's an incredibly fascinating world. So it is only about 800 miles across. So it shouldn't be visible in a small telescope, but it is. And it's because it's got a coating of ice that makes it really bright. And then as we sent probes there, we found that the reason it has this coating of ice is because it has an ocean underneath the surface. And geysers are shooting off from that ocean, breaking through the surface. And then as these geysers erupt, then the ice particles freeze out, settle both on the moon and on the rings as well, Saturn. And so this bright coating is making it visible. And of course, since you have a water world, there is a possibility that something could be living in that ocean. So that's something we definitely are going to return to see if we can learn more about that world. So really fascinating world for something so small. Titan is the largest moon of Saturn, and it's the one that's the most easiest to see. It's about 8th magnitude. It is the 2nd largest moon in the solar system. Only Ganymede's larger, and both Ganymede and Titan are larger than the planet Mercury. So they're pretty substantial bodies. And Titan is the only moon in the solar system that has a substantial atmosphere. In fact, its atmosphere is a little bit thicker than our own. And it's the only world in the solar system besides the Earth that has rain and has lakes. But the water on Titan is not made of the same stuff as our world. So the liquid there is liquid methane. So it rains methane, and the lakes are of liquid methane lakes. And water on Titan, because it's incredibly cold there, it's so far from the sun, water takes on the consistency of granite. So the rocks are water that's frozen super hard, and the rain is methane. So it's just absolutely fascinating where you get Earth-like features using different materials. But through the telescope, it's just fun to look at. You can watch it easily move around Saturn. This moon was discovered by Huygens, right? The same guy who discovered the features on Mars. And it takes about 16 days to complete one orbit around Saturn. So you can check in on Saturn from time to time. You can pick up Titan very easily, and you can watch it actually see its orbit easily as it goes around Saturn. So when I did this in 2007, I noticed that the motion was clockwise. So it seemed like Titan goes around Saturn in a clockwise direction. Though a few years later, I did the same thing again, and now Titan was going around Saturn counterclockwise. So at first I was confused, like, did Titan change its direction in its orbit? And I realized, no, it is that all objects, really, in the cosmos will go around something else, both clockwise and counterclockwise at the same time. And how it goes depends on perspective. So in this instance, if we're looking down on Titan, that is from the north, then it'll appear to have a counterclockwise motion. If you're looking up at Saturn and Titan, that is when the south is presented well to us, then it takes the opposite track. And so this would be true of like the Earth going around the sun. If you look down on the solar system from, well, what we would call the north, that is, well, follow the North Pole maybe up and look down, you'll see the Earth going around counterclockwise. But if we look at it from below, it'll have the opposite. So that was just an interesting reminder to me of motions, right, in the solar system. Right now, with the rings being tilted very close to zero angle, Titan is going to appear more like the moons of Jupiter, shuttling back and forth, as opposed to having a nice sweeping orbit. Now, the last moon we want to talk about is Iapetus. So it is much farther from Saturn than the other moons are, so it's harder to pick out for that reason. But there's another thing with it. When it is furthest west from Saturn, and again, this is the south up view, so west to the left. It's at western elongation. It's pretty bright enough where you can pick it out in a small scope. But as it swings around to the east, then it virtually vanishes from view in small telescopes. And so astronomers recognized early on that's because it has two faces. So one is exceedingly bright, the other exceedingly dark. So when the dark side is towards us, it is difficult to see or vanishes in small scopes, while when the bright side is towards us, you can pick it out. So that's kind of cool. We have had probes take detailed photos of Iapetus. It proves that point. One hemisphere is much darker than the other, and we're still trying to figure out exactly why, though we have a few theories of how this could have happened, but it's kind of fascinating too. And so that's kind of cool to check out. So now let's look, the last slide for today is let's look at Saturn itself. So again, like I've had with Jupiter, it's like rewarding to look at it over time. So right now, it's going to look like the 2010 presentation, kind of the rings flat. It'll be pretty flat right in March of 2025, so just in a few months. So at first you might think that's disappointing, but it's actually kind of cool because it doesn't present itself that way to us all that often. Most of the time you can see the rings in some fashion, right? So it is kind of cool to see it this way. You can notice that it has cloud belts too, like Jupiter does, but it doesn't have the colorful spots that Jupiter has. So it's much harder to see those on Saturn. There's one feature called the Great White Spot that appears maybe once every 30 years or so. But other than that, it's hard to pick out details on Saturn. So each planet has its own characteristics. But of course, the rings are beautiful, and this is like kind of cool to see. So it's definitely worth checking out. And then you can make a note or sketch again of this. And then you'll be rewarded over time as you go to check on Saturn over the next few years. So what will happen again is, so Saturn appears this way because like Mars and the Earth, its axis is tilted in a 20-some-odd degree angle, causing seasons. So Mars and Saturn and Earth all have seasons. And when you have an equinox, then it's going to appear like this, where neither pole is tipped towards the sun. And since we're close to the sun from Saturn's perspective, neither pole will be tipped close to us. But then as the seasons change on Saturn, then the poles start tipping. So here we had, this is south up again, so here we had the northern hemisphere come to its northern summer, so we could see the northern side. Now you can see details like the Cassini division and the rings, and then it moves back to here and then moves so that the southern part is going to be visible towards us, right? So you'll notice over time how the perspectives of the rings change.
How long does that take?
So it takes 30 years to complete an orbit, so it'll be 15 years between each season, right? So, but you see already here, this was just 2 years later after the equinox where I could already begin to see the rings in detail. So that means 2 years from now, it'll look something like this. And then just 4 years from now, it'll already start opening up pretty wide. And it'll keep opening up even wider until the equinox start to change again. Right? So then it doesn't even take the full 15 years to get this effect, which is nice. So again, get out there, take a look at it, appreciate this edge-on view, and then you'll appreciate these changes that you'll see in just the next few years as we go on. So that concludes my tour of the planets for tonight. Does anyone have any questions?
What are the rings of Saturn made of?
Oh, so that they're made of just individual particles, really. So they believe that a moon strayed too close to Saturn and tidal forces broke it apart. That's one theory. And so you had a moon just get disintegrated by these strong tidal forces of Saturn. And so all these chunks then are in orbit around Saturn that creates the rings. And then you have the other moons of Saturn tugging on the rings. They tug to pull them out, while Saturn's tugging the other way to pull them in. And that creates gaps in the rings, the most prominent being this one, the Cassini division, right? So, so they're all just a swarm of very small boulders and such from this destroyed moon. And they're thinking now that this might have happened in more recent geologic times, only a few million years ago, as opposed to when Saturn first formed, so that the rings are a more recent phenomenon for Saturn. They also believe that Mars might have a ring once Phobos gets shattered. That's one possibility as it moves too close to Mars. But it won't be anything as dramatic as these rings here.
So there's no ice?
So there would be ice, yeah, because the moon itself would have been an icy body with lots of water. And also like Enceladus, as I mentioned before, will be having ice flow out from it onto the rings. So that will help the reflectivity of these boulders and particles and make them so bright. Yeah.
Right, for Mars, because with Jupiter, the quick rotation, like you can catch it a red spot, or if you miss it, it's like a couple of days or so. But since Mars' kind of rotation is only a little bit more than like 24 hours, how do you get to catch some of the different features? I mean,
Right.
would it take like
Oh, it's a great
long
question.
time?
So it will shift 9 degrees per day. So it means in 40 days you can see completely around Mars. So you can check in then like from week to week, and then so you'll see if you're looking at the same time, right? You can see the features slowly drift in and drift out of view.
He doesn't sleep, he's up all night.
Another planet does Uranus have a ring too? Or
Yes. So they found that Uranus has a ring, Neptune has a ring, even Jupiter has a ring, but they were made from much smaller moons, if that is the process, and so they're much fainter and not anything like Saturn's. And so we're not able to see the rings of those other gas giants with an amateur telescope. They discovered the rings of Uranus when it occulted a star. That is, as it moved across a star, they noticed the starlight being interrupted prior to the planet itself crossing the star. And so that's where the original discovery was made. And then the Voyager probe had beautiful images of the rings of Uranus, and now great images from James Webb. You can find online of the rings of Uranus, but you need help to be able to see them because they're through technology, because they are really so faint. So it has to do with how much material do you have to create a ring in the first place. So with Jupiter, it was with Saturn, it was unusual because it was a really large moon that got destroyed through these tidal forces to make something so substantial and beautiful.
Ron,
Mm-hmm.
Curiosity about your process
Mhm.
of drawing.
Yeah.
It occurred to me that, I mean, I know how wet equipment gets during the night, so
Mhm.
how are you trying to make, and I'm assuming you're using like pen and paper or
Pencil.
paper?
So pencil. I have a notebook and a pencil. And well, dew can be a problem sometimes, but not always. There are many nights where at least it's not where my paper is getting soaked, right? But so for most nights I've been fortunate. I can just sit outside and make my sketches. I'll have like
You don't have to like cover up or anything, or like when the bugs start bothering you?
Well, I have a black cloth I'll put over my head. It would help block stray light, and then that can help if you got bugs, right? And then, yeah, I would, for the most part, I haven't had much issues with dew with the paper. It'd be that way if you had a very bad night of that, right? It'll start to affect your eyepieces usually more first, yeah. Yeah.
Your illustrations are just phenomenal.
Oh, thank
I would
you.
imagine you started this, when you were younger.
Yeah.
The amount of time you spent drawing these, you must get some really satisfaction. I always think, would you rather just take photographs of it, save you a lot of time?
So with the planets, I've gotten used to this very much. And so I would not do photographs or imaging. I prefer to do drawings. And one reason I prefer to do drawings is it's because then it trains your eye to pay attention to what's there. Like I had mentioned, which I wish I had uploaded my slide of Mars properly, but like when I noticed that feature on Mars slanting to the east, right? I mean, it's a subtle thing, but that is because you're making a drawing. And so you have to say, how do I draw it? Oh, then you notice, right? It's not just straight up and down, it slants. Then 50 years later, little did I know it would pay dividends where I'm like, wow, this has changed now from how it was before. So it's like you're picking out things you would otherwise overlook. So that's why I like drawing.
And it's incredible.
Yeah.
So when you're doing like something like Jupiter,
Mm.
it looked like you had guidelines for the latitudes.
Yeah.
Do you plan that out ahead, or do you just?
So I did. Like first I'll make the quick sketch on site, and then I will go back with my drawings and then clean it up. And then and I'll do mental notes then. So if you have a belt, where do you position it on Jupiter? How high, how low, how wide is it, right? And so on. One thing I could point out with Jupiter, like the cloud belts, they change. Like here, Saturn has one like this. With Jupiter, this belt is usually the thickest one. It's the south equatorial belt. But sometimes it becomes pencil thin. My drawing actually showed that. And that was cool, like the 2010 view, if I go back to that. So can I reverse it? I don't
Hang
know.
on a sec here.
Okay.
Got it.
Oh, here we go. So, like here, look how different that belt is here compared to like here or here, right? So this really happens from time to time. And so it's things like that then that when you're making drawings where it helps you pick up on, what features that you'd otherwise overlook. Yeah.
Are Saturn's rings currently coming into Saturn, going out from Saturn, staying where they're at?
So that's a good question. I think they would be falling into Saturn, if anything. And they do believe they will disappear, but it will still take like thousands, 100,000 years, if not more, which is good because I love Saturn's rings. I want them to stay around for a while. But it's, you know, we learn like they're not permanent like we thought they might be. Right?
Second question then,
Mhm.
if you could go back to 1972,
Mhm.
what would you change in your observations?
Oh, so there I was just starting out, right, as a kid. So what I would change, I would have done more deep sky back then. So that would be not so much the techniques I used, because they were kind of working, right? Other than you just your skills get better. But that's a good question in terms of like, why did I love the planets so much? It's because they're easy to find. I didn't have to travel far. And I didn't have to go through a lot of effort to search things out, right, for like a deep sky object. So they're just there. And they keep changing all the time. So you're rewarded, like instant gratification, right? And so that was my first love of astronomy, was the planets, right? Really accessible and showing you a lot very easily, right? So what I would do different back then is to start my deep sky, you know, sooner, because that's a whole different thing, but wonderful in itself. Now I just love doing my deep sky work, right?
Have you ever tried like white pencil on black paper?
Yes, I have.
Yeah.
So more with the deep sky, I've tried it, but I've never been quite as happy. Some people do a great job with that, I see, you know, and I'm not a great artist, so.
Is it easier to do the faint fuzzies with the white on black?
Yeah, the faint fuzzies, definitely, yeah.
Okay.
Mm.
Ron, I was looking at some of your magnifications on Neptune and Uranus, and you were getting to about 300.
Mm-hmm. Yeah.
Anytime I tried to get that high, I've always just seen them bouncing. So I don't know if it's just,
Well, seeing conditions are everything, right?
I guess, the patience of getting it away from the, horizon, or.
Well, that's the key. So if it's well placed in the sky and it's a good night, okay. So here's another thing I noticed with that, right? So now I live in the city. I live in a high-rise in downtown Chicago overlooking Millennium Park. So I can get to my job easily, and it's fun to live there. But I miss my astronomy, so I started getting my telescope out on my balcony, and I found now suddenly I could see some stuff. And then recently, in the last couple of weeks, we had some really clear nights. And I took my scope. I've been finding carbon stars, so I'm seeing new objects, which is cool. But then I looked at the double-double, right, in Lyra. And then I had to get high magnification. So I did get to like over 200 power, right, to split the double-double. But and so here you have the most horrible light pollution you can imagine. And yet it's like it was great conditions, great transparency, great seeing. And so in spite of that, I'm splitting the double-double with high power on a balcony in Chicago, because that has a lot to do with just what are your conditions. So, if you get great conditions, even in very bad locations, you can use high power. But then you can be in a great location and have bad conditions, and you just can't resolve it. It's always going to be swimming, and like getting bloated and whatnot, and you're done, right? And there's nothing you can do. So it's the sky, right? Okay, any others? So, well, thanks a lot, everyone, for showing up. This vacation start. So that concludes, and then we'll have fundamentals next month, though I'm still trying to kind of figure out exactly what that would be. I have kind of one idea. Maybe I'll talk about telescopes, buying telescopes, as we're getting into the holiday season. So that's my thought for now. But anyway, thanks a lot.
Thank you.
And Ron.